Hi guys, in this video I'm going to talk about generalization and the bias-variance trade-off. So generalization is a general topic that applies not just to neural networks, but to all forms of regression, classification, and machine learning. And what we want when learning a model is that on the one hand, that our model is expressive enough to actually model the underlying process. And in that case, we say it has a low bias and it doesn't underfit. And the second thing we want is we want our model not just to perform great on our training data, but also to perform great on other data that it hasn't seen, on new data. So we say we don't want that our model overfits to the specific data. And we also call this that our model has low variance. But it turns out that we want these two things, but up to some level, there is a trade-off between the two. So if we want low bias, we might get high variance. And if we want low variance, we might get high bias. So let me state again what is bias and what is variance. So suppose we have data represented by these blue circles. And suppose that the true underlying structure is this green curve over here. If our model is too simple, it's not complex enough. For example, if we are just using a linear regression, we're just fitting a straight line, then obviously it cannot fit to this data. Suppose we also have another point here and another point here, and another point here, and maybe there's also some noise. Maybe there's some points here, but it's quite obvious that a straight line does not fit this data. Okay, and this means that we have a high bias. We are unable to capture the true structure. What variance is, suppose that our true structure is something like this, but there is some variance to the data, and it's can be represented by these two curves over here that represents the variability interval, yeah? So our data actually comes from, we can have also data here and here, but suppose that one time we draw the data and we get these blue points, and now we are fitting our super expressive neural network to it, and it fits this beautiful orange line to it, and we think, oh, great, we found a great model. But actually, if we were to draw a new set of data points, we would get these red points. And then our neural network, this orange line, is not really fitting to the red points. So this is what variance is. It's that we are overfitting to a specific data set, even though if we had more data, we would see that we are actually not fitting the true process. So this is one form of variance. Another form of variance is to overcomplicate things. So suppose that the true process is this orange curve, but our model is so complex that it does something like this. It goes like here and here and here and here and here and here and here. Okay, so obviously it doesn't look so good, right? I mean, our model clearly it tries to pass through all the points, but it does it in a really bad way. So it overcomplicates the situation. The situation is much simpler. So usually there's a need to find a balance or a sweet spot where we don't overfit the data, but we also don't underfit it. So in this graph over here, looking at the data, the blue points, the orange line seems to underfit the data. The red line seems to overfit the data, but the green line seems to be just right. This is just from eyeballing the data. Now, I want to dive deeper into the mathematics behind the bias-variance trade-off. We will define a generalization error, and then we will show how it's actually comprised of the squared bias and the variance. So suppose that our true model is something like this. We draw data. We have data that comes from some function. We call it mu of x, plus some noise. There is some stochasticity in our data. So if our noise is a Gaussian with a zero mean and some variance, then our y will be distributed normal with the mean function. Yeah, for each x, it will have a different mean and some variance around it, some noise around it. Now we try to estimate this value, the true mean, using a neural network. We will denote it by an f. And now if we look at the MSE, the mean squared error, between our neural network f and the true mean mu, and so this is the error, we square it and we take the mean of it, and this is the mean squared error, we will now show that it's equal to the bias squared plus the variance. So what we will do, we will first subtract and add the mean of f. So f is also stochastic, right? It depends on the specific data that we have. For example, in linear regression, f is equal to this using the normal equations. And since this is random, then f itself is random. Okay. Likewise, for neural networks, we also have the stochasticity that comes from having a specific data set. So if we give a specific data set to the neural network and we train it exactly the same, we initialize the weight the same, we train it for exactly the same time, then we will get a certain f, right? We'll call it f1. But if we'll give it another data set, even though if we train it exactly the same, we will get a different function, okay? So there is some stochasticity for f, and this is why we can say, this is why we are taking the expectation with regards to f. Okay, now I will call this thing a and this thing b, okay? And I'll square it, so I'll have a squared, b squared, and 2 times ab. Now an expectation of a sum is the sum of expectations, so we'll take the expectation with regards to each element here. The first element is just by definition the variance of f, okay? So we will denote it by the v of f and we will keep it all the way through. The last element, we notice that actually nothing here is stochastic. So mu is not stochastic. Suppose that we have access to it, it's just some fixed function. Once we take the expectation of f, we lost the stochasticity. So there's nothing to take the expected value with after that because this whole thing is a constant. So this expectation terms cancel and we are left with this. And notice that this is the definition of a bias, right? It's just the expected value of the function minus the true value. And we square it, so we get the bias squared. Now what happens to the middle term? Well, the only stochastic part here is f. Once we take the expectation with regards to it, we get e of f minus e of f. So they both cancel. And then this whole thing becomes 0. And so it cancels out. And so we proved that looking at the mean squared error is equal to the variance plus the bias squared. And the mean squared error in this case is our generalization error. Notice that both terms are positive. The variance is always positive. And here we square the bias, so it's also positive. And we want to minimize both. And the way it's usually depicted, if we are graphing the errors as a function of the model complexity, then usually if we increase the complexity, the error goes down for the bias, but the variance goes up. So we have to find this sweet spot where the model is complex enough to have a low bias, but not over complex to have a high variance. And then we are finding the optimal model that minimizes our generalization error. Now, how do you detect that you have generalization errors? So I've shown you 2 methods, but they're both not applicable in real-world situation. The first one was eyeballing the regression curve, or you can also eyeball the decision boundary in case of classification. And I showed you, okay, this looks too complicated, this looks too simple, this looks just right. You can't usually visualize in real-world problems because the models are too complex in high dimension. It doesn't work. The second thing I've shown was, let's look at the bias variance, compute the total generalization error and find the optimal point. We also don't have access to this, right? I mean, here we are assuming that mu is somehow known and we have access to it and we can compute the mean of f and the variance of f. We can't do this in real-world application. We can't train a neural network and then draw new data, gather new data and train new neural networks on them and do this a lot of times and then average them to find the mean and take the variance of them to find the variance. This is not applicable for real-world problems. It might work for simple problems where you can simulate a lot of data quickly, but it doesn't work in the real world for real problems. So what do you do? Well, what you do is you divide the data into 2 parts. One is the train part. It's usually the larger part, and you train on that part. And the second part is the validation part. And you measure the error or the accuracy or whatever metric you're using on both the training set and the validation set, and you measure it through time. And you measure it and you measure it, you measure it, and then you get to the end. And if you have a high training error, and what is a high training error? It's all relative. It differs from problem to problem. But if you have a high training error, it's an indication that you have a high bias. So your model is just not good enough. It doesn't manage, even on the training data, it doesn't manage to get good results. But if you have a validation error that is even larger than your training error, then this is usually an indication of high variance. So this is an indication that you're not generalizing well and that you're overfitting to the specific training data. And another thing that you usually do is you do this across time or across training periods. So if you have here some training periods and here you have the error, then you might see that this is your error for the train, but this is your error for the validation. Okay, and then you say, okay, at some point, our model is actually, our validation error is starting to get bigger and bigger. Maybe we are overfitting the training set, but we are actually not performing well on new unseen data. Okay, so this is how you detect it. What do you actually do to overcome this? Well, to decrease the bias, you mainly need a more expressive neural network. Maybe more neurons, more layers, different activations, different architecture in general, etc. This is your main tool. Maybe you need to train longer. So maybe you have a great network, but you just unlocked its true potential and you need to train it longer in order for you to access that great potential. And the third thing is also not always applicable, but maybe if you have some prior knowledge about the true structure of this new function that we are trying to fit. So maybe you know it's a composition of 3 functions, so 3 layers of neural networks. So whatever knowledge you have maybe about the true structure can help you create a better architecture and then decrease the bias. Now, how do you decrease the variance and avoid overfitting? One of the most popular ways is adding regularization. And there are 2 main types of regularization that are often used. The first one is the L2 norm, or the weight decay, which adds a penalty to the original loss function that depends on the weights of the neural networks. And because it adds this penalty, it encourages the model to have smaller weights, which prevents overfitting. A second form of regularization is called dropout. And what dropout does, it randomly chooses neurons in your neural network and it shuts them down. It closes the activations and it also closes all the connections. It basically zeroes them out. And this also improves the variance and avoids overfitting. There's 2 main views of what is going on there. First is that it makes each neuron more dependent on itself and not rely on other neurons. So it avoids what is called co-adaptation. And a second way to look at what is going on is that in each round of training, you are basically sampling a sub-network of the total network. And each of these sub-networks is giving you some results, some weights, and you're kind of averaging them out in the end. So you're doing this, so you're training for many rounds, and then your final results, what you get is sort of an ensemble of the previous networks, an ensemble of experts. And it is known in general that ensemble methods have lower variance and are more robust. Another thing that you can do is called early stopping. And going back to this graph over here is noticing when your validation error stops improving and actually starts to get worse, and in stopping the training there. So avoiding a case where you're going all the way here. Okay, so maybe you will stop here. You see, okay, yeah, we didn't improve for a long time. We stop here. And this model is actually better than if we go more and more and more and we stop here, because here, this is our estimation of our generalization error, and it's much greater than this amount over here. And this is called early stopping. And the fourth and final thing that you can do is, of course, get more data. So if you have more data, it reduces the risk of fitting a specific subset of the data and just makes it more reasonable that we are actually fitting the true process and not some subset of the process. So in this example over here, if we had more data, if we had a lot of data, then maybe we would fit something like this. And this is probably more plausible than this orange curve or this incredibly complex red curve. And I will go into these 3 methods in subsequent videos, but this is all for this video. I hope you enjoyed and see you in the next one.